Hello everyone. This video presents a report on a paper published in the IJECE journal. My name is Mohammad Ahmadi and I co-authored this paper with my advisor Dr. Rouhollah Dianat. This paper is one of the works derived from my thesis at University of Qom in Iran. The GitHub repository link of source of my paper is provided here in the first slide. The topic of this paper lies in the field of image processing and face recognition, and its exact title is Efficient Smart Distributed Face Identification using the MixMaxSim decision function. Uh, This presentation includes the following sections: introduction, related work, proposed method, experiments and results. As you know, face recognition, like many objects in image processing, faces numerous challenges. For instance, lighting conditions and image resolution can significantly impact the results. Additionally, images may be captured from the front or side, and the age of individuals in different images may vary. Furthermore, the amount of makeup, clothing, or facial hair can differ across images. We may have more images of some individuals in our dataset while having fewer of others. Sometimes the similarity of one person's image to another person's image may exceed the similarity of their image to another image of themselves. All these challenges are exacerbated when the number of classes becomes very large. Therefore, in this paper, we specifically focus on the challenge of large scale. This challenge is further divided into three sub-challenges: accuracy, time, and memory. Naturally, as the number of classes increases and the number of images per person becomes insufficient, the likelihood of overfitting increases, leading to higher error rates and reduced accuracy. On the other hand, when the classes are trained together in a single network, the number of parameters become very high, especially in the penultimate layer, which is typically fully connected. Maintaining all these parameters simultaneously can be impossible if the number of classes is excessively large, and it also results in high temporal complexity. This paper claims that the proposed method addresses all three sub-challenges simultaneously. Related works. Various methods have been proposed to enhance the performance of face identification systems. In this paper, we categorize these approaches into three distinct groups. Group 1: methods that propose newer and more accurate loss functions to increase accuracy. The most well-known among them are contrastive loss, triplet loss, center loss, marginal loss, L softmax, A softmax, norm phase, arc phase, S phase, ghost phase. The main issue with the existing methods in Group 1 is that if the number of classes exceeds a certain threshold, i.e., the limits of available memory, their implementations become unfeasible and also increasing the risk of overfitting. Group 2 methods proposed to facilitate the implementation of face recognition at large scale, thereby addressing the memory issue. Some of the most significant methods include dynamic active classes selection, distributed arc face, softmax dissection, negative classes sampling. These methods typically reduce recognition accuracy but enable the implementation of face recognition systems at large scales. And Group 3 methods aimed at increasing accuracy in large-scale face identification systems. Some of the most important among them include multi-input models with different poses or crops, error-correcting output codes or eCOG, label mapping, independent softmax model or ISM, and multi-cognition softmax model or MCSM. To save presentation time, we will refrain from elaboration on the aforementioned methods. The proposed method of this paper is based on the independent softmax model. In this method, all classes are initially distributed randomly among different subnetworks, and each subnetwork is trained independently. Then the test image is fed uh, into all subnetworks, and the class with the highest softmax output is selected as the chosen category. However, this method has a fundamental flaw arising from the random distribution of classes among the subnetworks. This flaw is observable in the figures. The left figure represents a lucky or fortunate scenario in the independent softmax model. Suppose there are a total of four classes. Three are very similar, the real, messy, and two individual closely resembling Messi, and one category or class is Ronaldo who bears no resemblance to Messi. If the random distribution of classes is such that the test data is the real Messi image, the first subnetwork will yield very close scores, around 50% for both similar classes. In the second subnetwork, since there is competition between the real Messi and Ronaldo, it is evident that the second subnetwork will give a high score to the real Messi and a low score to Ronaldo, who bears no resemblance to the test data. Ultimately, the real Messi is selected, which is an accurate choice. However, if the distribution of classes is like the right figure, the network will mistakenly select the fake Messi rather than the real Messi, which is an incorrect choice. This issue arises from the random distribution of classes among the subnetworks. Our proposed method aims to mitigate the negative effect of randomness by using clustering for category distribution. This method consists of three phases. Phase 1, preprocessing. In this phase, classes are assigned to different subnetworks using clustering. Phase 2, processing. Each subnetwork is trained using training data relevant to its assigned classes. And phase 3, post-processing. This phase involves decision-making, which is the most critical part of the paper and consists of three modules: toilers module, similarity-meter module, and final decision-maker module. As you can see in the figure, toiler's module for each input image. This module determines the model output value for all classes across all subnetworks and introduces a candidate for each subnetwork. Second module, similarity meter module, for each input image. This module determines the similarity of each class to the features of the input image and introduces its candidate. And finally, final decision maker module. Each of these two modules scores each other's candidate. Ultimately, the class chosen will be the one that maximizes the product of the model's output value and their similarity scores. In other words, we will have two candidates and four values. First candidate uh, is related to Toiler's candidate. We name it X with model output value A and similarity value B. Second candidate, similarity candidate, named Y with similarity value C and model output D. Ultimately, the category chosen will be the one that maximizes the product of the model output values and their similarity scores. Another point is that since the scales of the neural network output values and the similarity values differ, we decided to define a weight for the toilers module candidate to enhance the system's accuracy. The weight was derived using validation datasets, and it was observed that the best weight value for the validation dataset also performed best for the test dataset. To achieve this, we considered 200 values between 0 and 2, and at each point where the system's accuracy was optimal, the point was taken as the weight for the toiler's candidate. If we set the weight to 0, it means that only the similarity meter module influences the final decision, similar to using K and N. And if we set it to 2, it means that the output values of the toilers module are influential. However, the combination of these two yields a result better than either alone, resembling ensemble learning. Our experiments were conducted on the following well-known datasets: VGGFace2, MSCeleb 1 million, and GLint 360K. We used the following uh, extractors for feature extraction: ArcFace, S-Face, Ghostface. These methods are among the latest. To demonstrate that the proposed method performs best, we compared the following scenarios. First, distribution free, which has no distribution. Second, random distribution and max decision maker, a distributed network with random distribution and max decision making, such as independent softmax model method. And three, cluster classes and max decision maker, a distributed network with clustering and max decision making. And finally, four, cluster classes and the MixMaxSim decision maker, a distributed network with clustering and MixMaxSim decision making. The proposed method MixMaxSim is mixture of max and similarity. To increase the speed of the algorithm, another improvement was introduced. In our experiments with 20,000 classes and six subnetworks, it was observed that in over 80% of cases, the maximum model output scores was above uh, zero point 0.5, and nearly all of these selected categories were correct choices. Almost all error occurred in instances where the model output score was below zero point 0.5. Thus, it was determined that when the model output is below zero point 0.5, it represents a region of uncertainty. For cases where the model output score is above zero point 0.5, we only utilize the toilers module in decision making, and to increase speed, we only use the similarity meter module when the module output score